Good evening, ladies and gentlemen. First, my first language is not English, so I apologize in advance for any confusion or any injustice to the language. This paper is about characterization of experiments on spline couplings with the help of principal component analysis. This is relatively less used and less applied technique to analyze these experiments. Our ultimate aim of research is to be able to model and predict fretting, fatigue and wear. Fretting is basically mostly a quasi-static process, and it is a result of repeated relative surface movement of components which results in wear and fatigue. It results in high temperatures, then oxides are formed, rusting, and finally the surface is damaged. Its significant disadvantage is that it causes a huge reduction in the fatigue life. Classically, we would see a typical SN curve where we will see that for a particular stress, these many number of cycles are required, after which the material failure will occur. Unfortunately, when the stress is of this kind, that it is repeated relative surface movement, that is the fretting fatigue or fretting wear, then there is no such criteria or data available to accurately predict that after how many cycles this will fail. So the ultimate aim is to be able to devise something of this sort, keeping in mind all important parameters which are important in case of fretting, fatigue or wear, and then predict that in working conditions after these many cycles this material is expected to fail. In this particular research work, my aim was to characterize the fretting wear experiments. We have got an apparatus which is coming next, and we have performed various experiments, and we have interpreted those experiments using principal component analysis. The most important parameters in fretting wear are the pressure distribution, revolutions per minute, the rotational speed, applied torque, misalignment between the shafts, friction, materials properties, foreign elements, corrosion properties, temperature and vibrations. So next is our test bench. This is a quick summary of the test bench which we have used to perform these experiments. It is capable of acquiring data in real time, and we have performed tests for temperatures, misalignment, RPM, strain, torque, force, and LabVIEW was used as the tool to acquire the data in real time from the apparatus. And this is the summary of test bench functional specifications. It had the maximum RPM of 2000, maximum torque of 5000 Newton meter, inclination of 10 minutes, increment of 0.5 minutes, maximum oil temperature circulation in the circuit of this apparatus was 60 degrees Celsius. Oil flow rate was designed for 1 liter per minute, and the motor power was 6.3 kilowatt. This was a significant thing that in this apparatus the power of motor was being recirculated. So it resulted in quite low power requirements as compared to other test apparatus to test the fretting, fatigue or wear. Now something about the test article, the sample on which we performed these tests. We performed these tests on spline couplings, which are frequently used in aerospace industry. We specifically got some test samples from Avio. We performed the tests on those samples, and they are used to connect between the shafts and used to transfer torque and power. The design specifications of the spline couplings are given here, the type of material, the teeth profile, number of teeth, modulus, pressure angle. And in this case again we were looking for contact pressure, torque, RPM, misalignment between shafts, etc. This was our proposed methodology. After performing the test, we got a huge data. many parameters, thousands of readings, thousands of values. It was difficult to interpret or make some sense from the data directly. There were certain solutions available: principal component analysis, Fourier and wavelet transforms, artificial neural networks, but we went for principal component analysis in this particular work. We identified important variables. We discarded other variables which were less significant after the analysis. And in the next stage of our work, we are going to design the future experiments based upon the observations we obtained in this experiment. That will result in a less cost and a high time and a less time for the future experiments. And we will be able to process those data more quickly and with less time. And then we can finally even go for the models based upon PCA. Now just a quick review of the models we used in this particular work. In the first step, we acquire the experimental data. We inspect the variables, and if any variables are appearing similar, their trends are similar, we combine them, take the average. So it reduces the data in the first step. If the units of data are hugely different, their scales are hugely different, then we z-scale the data. We basically scale the data, and that is a very simple process that you subtract mean from every data element and divide it by its standard deviation. So that scales the data and brings it onto the same scale. Second step was that we find if the data variables are not very dissimilar, we can directly find the covariance matrix. If we scale the data, the covariance matrix is called as correlation matrix. We find eigenvalues and eigenvectors for both cases. The eigenvalues and eigenvectors with most values, with biggest values, are the most important parameters or the most important characteristics of the experimental data. Others can be discarded, and the most important with highest eigenvalues, they can be kept for further analysis. And that process of dropping the less significant and keeping the most significant parameters is called as feature vector. And ultimately we multiply this feature vector with the original data. So let's suppose we initially had 8 variables. After performing PCA, we are left with 2 variables only. So that is a very direct, immediate consequence, an immediate advantage which is visible. And finally, in this work, we use both approaches. We use the covariance matrix as well as correlation matrix. And finally, then we perform the comparison and analysis, and then we validated and interpreted the results practically. Okay, review of PCA I am going to skip because of the limitation of time, because that is already another field, established field, that is not something on my credit. But if anybody is interested in the question answer session, I can explain something about the how PCA works and everything. I will directly go to the next portion, that is our findings. First of all, something more detail about the schematics of our experimental operators. So here you can see that there were different temperature sensors, there were RPM sensors, torque sensors, actuators, reaction force, load cell parameters. So these were the things which were interfaced with the computer with the help of LabVIEW test board, LabVIEW data acquisition boards, and we recorded them in real time. So what we did was, we installed the hub and shaft of a spline coupling, applied certain torque on it at certain RPMs, and we kept on recording these different parameters, and later on we did this analysis. So this was preprocessed data. These were the important parameters which we identified from the experimental trends and behaviors: temperature, force, LVDT readings, misalignment angles, oil flow rate, then number of RPMs, torque, and then actuator motor RPMs. Okay, this is the most important feature in the first step. After you apply the PCA, after you find the covariance matrix, you get a result something like this. And this is the strength of this approach as well. This is not specifically applicable to my particular problem. It is applicable to any problem where you are interested in finding some mathematical correlation or model based upon experimental data alone. So how to interpret this? On the both axes, x and y, the same variables and their relationships with each other, they are shown in this, and these relationships are symmetric. And whenever, for example, in this block you see T and T, so this is basically covariance. Otherwise it is, this is variance, otherwise it is covariance. So when the variance of T with respect to T is taken, we say it variance, and when variance of T with respect to F is taken, we say it is covariance. Okay, so now you can see that most important parameters are shown in green or red. Red one are the negative and the green one are the positive. Now what does this mean? Negative means if one variable increases, the other one decreases. Green means if one increases, the other one increases as well. But here is a word of caution about PCA. This is a tragedy as well. It is possible that you plot a graph between the number of Facebook users for past 1 year and the grades of college students. Coincidentally, it is possible that you get a positive correlation. But does it make any sense? No. It is not directly correlated. Correlation does not mean a cause and effect relationship. However, absence of correlation or covariance means there is confirmed no relation. So this is an important distinction. I will want to repeat it to clarify it. If there is no covariance, there is no relationship. If there is a covariance, relationship may be present or may not be present. You have to further validate it. You cannot use it blindly. So this was an important point. Okay, now come to the principal components. As I explained earlier, that you get the eigenvalues for each principal component, and the most significant principal components are used, other one they can be discarded. Now the importance or the advantage in data compression, the memory savings you can see here. Original data was of 8 variables with 4, 1, 3, 5 readings, total readings this much, and the size in kilobytes was 132 kilobytes. This is just an example. And data after PCA, 33 kilobytes. You can see a huge saving of 75% in the memory requirements or the data processing requirements, and this is 100% recoverable. This is the lossless compression, you can say. Okay, just one slide is left after that. In this, we have identified the most important variables in our experimental data. First thing, we have discarded the least significant experimental data. That is another advantage. Third thing, we are able now to design next experiments with less parameters, important parameters, and also it would be done at the low cost. What is disadvantage is that typically these tests take 5 days, 7 days, 14 days to take some meaningful data, and we don't have so much time and so much resources to keep on spending and utilizing so many test samples. And next we have submitted these results to Avio, and we are going to receive the new test samples for the future work as well. Finally, we are going to mathematically model and simulate it and validate it. And now I am going to show you some of the important last few highlights. Here, after everything is done, we want to quantify the relationships. Now this is called as a loading plot, and this basically gives us the complete information about each variable. For example, without going into details of what each variable is, I am trying to convey the general idea that what does it mean. The variables which appear together, they tend to behave together. If one increases, other one increases. If one decreases, other one decreases. Second interpretation, further a variable is away from the origin. More important this variable is experimentally or statistically. Next, if these two variables appear together, they are behaving together. And these four variables, you can see they are appearing together near the origin. So this means these are the least significant parameters for our particular set. So, and we practically validated these readings as well. Interestingly, just to give you on the side note information, when initially I was provided this data, we were not told that what does this variable mean, to make sure that our findings are without any bias. Anyhow, so if there are any questions after this, I will be more than glad to answer them. And if anybody specifically wants to know about PCA